Right, hello Year 13. I'm afraid I can't be live in the lesson today because of dropping kids off at school and having to pick them up early at the end of the day. So I'm recording this lesson for my Year 13s Period 1 and also my Year 13s in Period 6. We'll go through any of those catalysis questions from last time. If you struggled with them, we'll go through them in the next lesson. Now I'm going to do a little standalone topic on transition metals. Very straightforward. It is colorimetry. Colorimetry, spelt in an annoying way. There is no U in the colour of colorimetry. Colorimetry is the use of colour or the intensity of colour of a solution in order to find out how concentrated it is. So the colour of a solution can show how concentrated it is. So the colour, in this I'm talking about the depth of colour. So how dark it is, the depth of colour of a solution can show how concentrated it is. Gosh, that's some very scruffy writing. All right, so what you need to know is you need to know sort of a basic idea of how this works, and then you've got to be able to answer a 6 marker on it, which is, you know, how can we use colorimetry to work out the concentration of something. All right, so I'm just going to reach through here for a prop. You all have inbuilt colorimeters inside your bodies. In other words, here we go, I'm just going to bring some of this here. Some delicious juice. Actually, I'm going to show it on the side. There we go. Some delicious juice. Now you're looking at this and it's Ribena, and you can look at that and you can decide from your experience whether or not you think that juice is going to be concentrated or not. So in other words, is it the juice like your mum makes when she wants you to not drink as much sugar and it's really dilute, or is it the juice that you get around your grandparents' house where it's so sugary that, you know, you can only manage half a cup? So I'm looking at that and I'm thinking, I reckon that looks fairly concentrated. My eyes are telling me that's fairly concentrated. I'll have a little drink. And I was right. That's really concentrated. You know, you can add water to it. There we go. And you can see that it gets more dilute. So your eyes are... So what's happening there is light is passing through that solution and it's hitting your eyes, and your brain is sort of making a qualitative decision on the concentration of that juice. So colorimetry is this process, but it generates numbers. So as opposed to just being a qualitative measure. More juice. That's spot on. Right. So what's going on here then? A colorimeter works by taking a solution and putting it in a special piece of equipment called a cuvette. Okay? I haven't got the tech today to do this, but if you just please Google cuvette so you can see what one of these is. A cuvette is somewhere where you put your coloured solution in here. Actually, I've got loads of colouring pencils because I'm at home and I have children. Okay, so you can have a colourful solution in the cuvette. What you do is you shine a light through that sample. Richard of York gave battle in vain. And you detect, so some of the light will be absorbed by this solution, and on the other side you have some sort of detector which detects how much light coming through. There's something that you have to realise first. Say in this example I've got a red solution. This red solution only really absorbs its complementary colour. So in that case, the complementary colour of red would be green. So to make a colorimeter more effective... Oh no, has that gone there upside down? I bet that did, didn't it? Oh well. I think we're back in the right way around now. So to make this colorimeter more effective, what you would need to do... Just checking I've got... I'm a little bit confused now where my Okay, so anyway, this is a red solution. So to make the colorimeter work better, we want this to absorb strongly. We want this to absorb strongly. So what we do is you put a green. You'd put a color here, a filter. Sorry, a filter of complementary color. So in this case, it would be green. So mainly green comes through. And then, because we know that colour is going to get strongly absorbed, and then some of the green light will come through and it'll be hit by the detector. And what the colorimeter does, it measures how much light is absorbed. So you often get an absorbance reading. So the program, the detector sort of says, all right, this much light came through. Then if you make this darker, I'll do that on here, a darker solution, even less light would come through. So a darker solution would absorb more and a lighter solution would absorb less. So the thing is though, there is no machine out there that directly links that you can plug in a solution and it'll just tell you the concentration straight away. A colorimeter will give you a random value for absorbance, but it won't tell you what that means in terms of concentration. So the way that you generate a concentration is to do the following. You firstly make up a range of known concentrations of the solution. So say for example we weren't doing Ribena, we were doing copper sulfate. You would make up some CuH2O 6 times 2, some copper sulfate solution, and you might for example make up some 0.1 mole per decimeter cubed, and then you might make up some 0.9, 0.8, 0.7, 0.6 and so on, and you make up a range of known concentrations of solutions. And then what you would do is you would, oh come on, so you made up a range of known concentrations. Then you would plot, oh no you wouldn't, sorry, make up a range of known concentrations, then you would put in colorimeter and read the absorbance. So you would then plot, so that would do that, then you would plot this graph. So number one, make up a range of solutions. Can you tell it's late at night and I'm trying to work this out. Number two, put in a colorimeter and read the absorbance for each one. Number three is plot, and this thing is called a calibration curve. So you would have the concentration of CuH2O 6 times here, ranging from maybe 0.1, what I've done there, 0.09, 0.08. I'm almost on the brink of re-recording this, but I've got to go to bed. So you do 0.01, 0.02, 0.03, 0.04, 0.05, 6, 7, 8, 0.09 and 0.1. So you'd make up all of these known solutions where you know the concentration for sure, you'd put them in a calorimeter and you would find that your most dilute one, this is absorbance, would have a low absorbance. The next one would have a slightly higher absorbance. The next more concentrated one would have a slightly higher absorbance, and then a slightly higher absorbance, and a slightly higher absorbance, etc., etc., all the way up to your darkest one, which would have the highest absorbance. And this, even though it's a straight line, is known as a calibration curve. You have just calibrated your colorimeter. The next thing you would do, so step 4, is put your unknown sample in the colorimeter. So you'll now have a little sample in a cuvette which you don't know the colour of. And what you would do, and it might give you a reading, so it will give you a reading, and maybe that reading comes out here. If it gives you an absorbance of here, this value, you know that its concentration must be 0.045. Alright, so it's a bit of a faff to use a colorimeter. You have to make up a range of known solutions, known concentrations, put them all in a colorimeter first, which gives you this curve, and then you put in your unknown sample. Once you put in your unknown sample, compare to the curve to work out the concentration. I know I've waffled, but there you go. That juice is delicious. Alright. So that's how colorimetry works. Now I used to have a job doing this between some years in my university studies, and my job was to go down to the rivers in Sheffield and test the rivers for their iron 2 concentration. Alright, so you take river water from places like Endcliffe Park, if you know it, in Sheffield, and you take buckets full of river water and then take them to the lab, and we would put that water in a colorimeter. So to find out how concentrated the iron was in the river in Endcliffe Park. So we were actually analysing the water for this complex, FeH2O 6 times 2+. So this is what you find in the rivers in Sheffield, and its concentration needs to be monitored. Now, there's a problem with this in that Sheffield river water, even though it's got this complex in it, this complex has not got a very intense colour. So it does, even if it's incredibly concentrated, it doesn't absorb very strongly. It's incredibly pale green. So you put it in a colorimeter and the colorimeter can't really pick up the absorbance. So what do you think we did before we put the complex into the colorimeter? Okay. Well, what we did was we added another ligand. And what that ligand did, you got a ligand exchange reaction. FeH2O 6 times 2+. We added some SCN-. Now, I know I'm going to make a mistake here because I can't remember whether SCN- is unidentate or whatever. So there will be a mistake on this. You'll have to look it up elsewhere. In fact, no, I'm going to pause. Right, I just looked it up and it's a bidentate ligand. Still might not be quite right, this, but what happened was we would do this. We would do a ligand exchange reaction. So by doing this ligand exchange reaction, minus, three minuses, 3 negative ligands, minus overall, and you would kick out 6 H2O. This was very pale green. We would do the ligand exchange and this was blood red. So you'd have the same concentration of iron, but you'd change the colour of it by doing ligand exchange. You'd change the energy gap, delta E. So you now had a blood red solution, which was much easier to do colorimetry on. So in an exam, the examiner actually, if they asked you how would you carry out a colorimetry experiment, there's actually, I think I just showed you 5 steps. Well, the first step is exchange the ligands to make the most intense colour. Let's go with more intense colour. Exchange the ligands to make a more intense colour. Number 2, make up a range of known concs. Number 3, put in colorimeter with complementary colour filter. Number 4, read absorbance and plot calibration curve. There for the known ones, this is concentration against absorbance. Number 5, put unknown in colorimeter Number 6, read, conc, off, calibration, curve. So that, like, you know, you get your unknown and it gives you a reading here. That's the concentration of your unknown. So 6 steps, 6 marks in an exam. All right. So that is how colorimetry works. Your eyes do it very, very quickly. You can tell the concentration roughly by looking at the colour that's going through a solution. A colorimeter does the same, but with the use of a calibration curve, it can tell you the concentration that you're dealing with. So, the final little bit on colour is you need to know a little bit about UV / ultraviolet / visible spectroscopy. Do we do that now? Nah, you know what? I'm not going to. Because... No, I think I will. No, sorry. UV and visible spectroscopy. So, different solutions, as we know, absorb different frequencies of light. So we are aware of this general rule of thumb that blue solutions absorb orange, for example, red absorbs green, and so on. It's slightly more specific than that, in that you can shine visible light or ultraviolet light through a solution and you get a very, very distinct spectrum. So I'm going to show you one here, and then I'll link to a YouTube video that does it well. Actually, I'm struggling here to get this done. It's late at night, so right. This is an example of a UV visible spectrum. So what's happened here is they've taken a sample of a transition metal and they've shone light through it. And each of these peaks represents where it is absorbing strongly. So it's absorbing strongly at about 650 nanometers, and it's also absorbing strongly at about 300 nanometers. And you can think of this as being a little bit of a fingerprint for this complex. I'm just going to find a UVVis spectrum on the internet by googling UVVis spectrum. So I'll show you this. Okay, so if you can see that, there we go, it's a bit better. That diagram that I've just shown you showed the complex was absorbing around about 650 nanometers. I don't know if you can quite pick that up on here. So what that means is it was absorbing strongly sort of this orange colour. Alright, it was also absorbing down in the UV region around about 300. But in the visible region it was absorbing around 650 nanometers. So when I look at that spectrum there, it means it was absorbing orange. So this is a blue solution that you're looking at. Now, different blue solutions like copper sulfate will have slightly different UV visible spectra. They will absorb slightly different frequencies of orange, and they will also have slightly different things in here. So they can be used to fingerprint colours or to identify compounds. There was a story that I remember reading in my last school where there was a really old painting that had been damaged. So I don't know, here's a painting. Let's make it look like the Mona Lisa. And it was all damaged. And they wanted to try and repair it. So what they did, there was this area here of it was the dress, I think, that was blue. And rather than just go, oh, we'll just go and patch it up with some blue paint from, I don't know, W.H. Smith, what they decided to do is they decided to scrape off the blue paint, a little bit of the blue paint, and dissolve it so you had a solution of the blue paint. You might know where I'm going with this, I don't know. They then performed UV visible spectroscopy, so they shone some UV and visible light mixed together through the blue, and they got a spectrum like that, where it absorbs very specific frequencies. What they could then do is they could then look at every single blue paint that they had in their stores or that they knew of, and they looked for the blue paint that had the closest match to this UV visible spectrum. And then once they had a paint that closely matched it, they used that paint to patch up the blue on there. So there's lots of examples of how UV visible spectra can be used, but it can be used to identify compounds by comparing them against known substances. So the frequencies at which a complex absorbs UV or visible light can be measured with a UV visible spectrometer. So the frequencies, the specific frequencies can be noted. UV visible light is passed through the complex, and frequencies passing through are detected. Those that not pass through are absorbed, and the point is it can be used to identify or to ID unknown compounds by comparing them against known compounds. Right, your questions to do as a follow-up for this. Question 27. If you have a look on here, you got question 27. You are provided with a 1 mole solution of iron 3 ions and a visible light spectrophotometer, a colorimeter. Outline a plan for experiments using this solution, which will enable you to determine the concentration of iron ions in a solution of unknown concentration. 5 marks. I've given you the schematic of how you do that, and it does include add a ligand to intensify the colour. So 27, I'm just going to do a quick look through. I'm going to pause while I do that. Right, I've looked through, that's the only one I can find on colorimetry, and I can't find any on UV visible spectrometry, but that doesn't mean it hasn't been questioned before. So what I'll do, so you need to do question 27. Clearly you've got to do that catalysis stuff as well from last time. I'll go through some of those questions with you, but hopefully this is a nice little standalone lesson for you. So just finished off now by doing question 27. I will also put another little video, if I can find a good one, about UV visible spectrometry, and I'll put that on this link as well. I hope that's okay. Goodbye. I'll see you next lesson.